Welcome to the Deep Dive, where we take the vast, often overwhelming ocean of knowledge and distill it into the sharpest, most surprising insights.
And today we are wading into some very deep currents.
We certainly are. We're talking about maybe the most recognizable scientist in human history, Albert Einstein.
His name is just pure resonance, isn't it? You say Einstein, and you immediately get this image of a playful genius, messy hair, and an equation that literally changed our universe.
Right, and our source material for this deep dive is just as vast as his reputation. We have everything from his core scientific papers, the ones that redefine space and time, all the way down to his deeply human philosophical thoughts.
And his personal quotes, which show this often contradictory view on things like fame and authority and global politics. It's a huge range.
That's right. We have a massive stack of material here. We're looking at his breakthroughs, his humanitarian work, and his often wry, sometimes, self-deprecating personal perspective.
So for you, the listener, our mission is pretty clear.
We want to try and construct a full biography of the man behind the physics. We're going to trace his journey from a completely unknown patent clerk to the scientific and cultural icon he still is today.
And it's such a profound story because his influence didn't just stop in 1915 when general relativity was finished. We are still relying on his work every single day, often without even realizing it.
That's what we want to get into. Who is Albert Einstein, really? How is his life defined by this relentless search for knowledge?
And what were his main breakthroughs? And what is his legacy actually doing in our world right now?
We're going to explore two essential sides of that legacy. First, there's the revolutionary scientist who gave us special and general, the absolute foundations of modern cosmology and technology.
And second, the deeply philosophical maverick. I saw one source call him a Korkhoff, a crosshead, or maverick.
Yeah.
And his personal ideals really shaped how he dealt with a world that was just insisting on turning him into this authority figure he never wanted to be.
It's that contrast, isn't it?
Yeah.
The contrast between those two lives, the theoretical genius and the humble, sometimes troubled man, that makes this deep dive so compelling.
Absolutely. So where should we start?
Let's start at the beginning. We're diving into part one, the man before the myth, 1879-1909.
Okay. So Albert Einstein was born in Ulm, Germany in 1879. And his early professional life, that decade before he became world famous, was anything but a straight line.
Right, it's a detail that often gets polished out of the heroic story.
Totally. After some initial setbacks, he was actually rejected the year before, he began his studies in mathematics and physics at the ETH Zurich in 1896, and he got his teaching diploma in 1900.
But that conventional academic path, it seemed blocked for him, maybe because he was, a bit of a nonconformist. He couldn't get a teaching job right away.
No, he couldn't. So the great incubator for his world-changing ideas wasn't some prestigious university lab.
It was a place of paperwork and bureaucracy, the Swiss Patent Office in Bern.
And that is one of the greatest ironies in the history of modern science. From 1902 to 1909, he worked there as a technical expert, basically just examining patent applications.
And this period was absolutely instrumental, but not in the way you think.
Not at all. He didn't have easy access to a full library of scientific journals or reference materials. And, counterintuitively, that might have actually forced him to think more deeply, more originally.
He wasn't bogged down by the existing dogma.
Exactly. He wasn't weighed down by institutional expectations. He had the time, and maybe more importantly, the mental space to think about the biggest problems in physics from the ground up without being, constantly bombarded by existing solutions.
The sources also note his job required him to get to the core physics of new inventions really quickly.
Yeah, a process that must have honed his ability to just extract fundamental principles from really complex details. He had a great mind, of course, but he also had this perfect, totally unlikely environment for radical new thought.
And he wasn't completely isolated. This is a key point. He had a vital collaborator, or as he called him, a sounding board, for all these wild ideas he was developing about light and motion.
That was his colleague, Michel Besso. And Besso was absolutely critical. While Einstein's work was deeply individual, it wasn't solitary.
So they would talk through these ideas.
Constantly. He later said he could not have found a better sounding board for my ideas in all of Europe. This dynamic, bouncing, world-shattering ideas off a trusted, critical friend, that was the catalyst he needed to refine his thoughts before he published them.
Let's talk about the man himself, the contrast between the private person who saw himself as just curious and the staggering public myth he became. We've got some fantastic quotes here that really reveal his core philosophy.
He had this incredibly humble, almost dismissive view of his own brilliance. He He famously said, "I have no special talent, but am only passionately curious."
That just reframes the whole idea of genius, doesn't it? It's not some innate, untouchable thing.
No, it becomes an act of profound, sustained passion and curiosity. It makes it human. It's about the relentless pursuit.
He also laid out his guiding principles, saying the ideals that filled him with joyful courage were simply goodness, beauty, and truth.
Yet he really wrestled with the sheer scale of the fame that his curiosity brought him. The world saw him as this oracle, but he often felt just misunderstood and completely overwhelmed by the attention.
There's that famous quote where he asks, "Why is it that nobody understands me and everybody likes me?"
That question cuts deep. It suggests he knew his physics was fundamentally hard for the public to grasp, but the image, the hair, the eccentricity that had become universally appealing.
And he felt the fame itself became a burden, that it actually corrupted his intellectual focus.
He really did. He observed, "I become stupider and stupider with fame." He felt the time he spent dealing with being a celebrity was time lost from the pure pursuit of scientific truth.
He also saw the irony in his own celebrity, especially given his youthful disdain for authority and establishment structures.
Oh, absolutely. He noted the absurd authority the public gave him, something he profoundly distrusted. He said, "As a punishment for my contempt for authority, fate has made me an authority myself."
He also joked about the media frenzy, didn't he?
Yeah, he lamented that, like the man in the fairy tale, everything he touched turned to gold, everything I touch turns into newspaper uproar. He truly saw himself as a simple philosopher who suddenly had everything he did exaggerated into this enormous public spectacle.
So we have this towering intellectual, but he's deeply suspicious of celebrity and authority. What about his core life philosophy? What did he really value outside of science?
He was a man of profound contrasts. He had a mind that could revolutionize the cosmos, but he paired it with these surprisingly simple, down-to-earth values. He genuinely believed that a simple and unpretentious external life is good for everyone, for body and spirit.
His goal was never material wealth or status.
Not at all. In fact, he considered things like possessions, external success, and luxury to be contemptible since his youth.
And he had a strong, active sense of service to humanity, which really informed his later political life.
Absolutely. He stated it plainly. A life lived only for others is worth living. That deeply humanitarian streak was always there.
And interestingly, the sources note that he found his greatest personal happiness in art.
That's right. He felt the highest degree of happiness with great works of art. And that reminds us that his search for truth in science was, deeply connected to his search for beauty and order in the universe. He was always looking for the elegance of fundamental laws.
That sets the stage perfectly for the ultimate demonstration of that curiosity. Let's move into part 2, the Annus Mirabilis and the Foundation of Modern Physics, 1905. If his life up to 1904 was the quiet prologue, 1905 was the explosion.
It truly was, a year that rightly earned the Latin title, Annus Mirabilis, the miraculous year. In 1905, while still clocking in at the Bern Patent Office, Einstein published 4 groundbreaking papers in the scientific journal Annalen der Physik.
And these papers collectively revolutionized science's understanding of space, time, mass, and energy. It's just staggering to think about.
One man, in 1 year, while working a day job, provided the basis for atomic energy, proved atoms were real, and completely redefined space and time.
Okay, let's unpack those 4 papers one by one. Starting with the one that, surprisingly to a lot of people, is what actually won him the 1921 Nobel Prize. Paper 1, the photoelectric effect.
Right, so this paper addressed the photoelectric effect, the observation that when you shine light on a metal surface, electrons get ejected.
And classical physics, based on Maxwell's equations, treated light as a continuous wave. So it had a big problem explaining this.
A huge problem. The wave theory suggested that if you just made the light beam brighter, more intense, you should eject more electrons no matter what color the light was.
But that's not what the experiment showed.
Not at all. Experiments showed that electrons were only ejected if the light reached a certain minimum frequency, a specific color, no matter how dim the light was. Below that threshold, you could shine the brightest light imaginable and get nothing.
So Einstein's solution was a radical conceptual leap.
It was a massive leap. He proposed that light energy isn't continuously distributed like ripples on a pond. Instead, it consists of discrete, localized packets, or quanta what we now call photons.
And he came up with the equation, EHF. The energy of a light quantum is proportional to its frequency.
Exactly. He insisted these quanta are localized at points in space, moving without dividing, and capable of being absorbed or generated only as entities.
So a high-frequency blue photon has enough energy in one packet to knock an electron out. But thousands of low-frequency red photons still don't have enough concentrated energy to do the job.
That is the core idea. It was a colossal jump because it flatly contradicted the reigning wave theory of light. And this work alone won him the Nobel Prize and became a strong indicator of wave-particle duality, this foundational idea that things can be both a wave and a particle at the same time.
Okay, moving on to the second paper, Brownian motion. This one is often cited as the definitive proof that atoms are real.
Yes. This paper tackled the erratic, seemingly random movement of microscopic particles suspended in a fluid, a phenomenon that had puzzled scientists for decades.
So he didn't just speculate about it. He actually quantified how these visible particles should jiggle around if they were being constantly bombarded by even smaller, truly invisible atoms and molecules.
He provided a mathematically testable prediction, and that quantification was the undeniable empirical evidence for the reality of the atom. Before this, many leading physicists, including the very influential Wilhelm Ostwald, they debated whether atoms were just a useful idea or actual physical things.
So this paper settled a fundamental century-old debate.
It really did. The source material specifically notes that Ostwald, a leader of the anti-atom school, was finally convinced by experiments that confirmed Einstein's predictions. This paper didn't just explain jiggling pollen grains, it established the atom as a fundamental physical reality.
Okay, now we arrive at the big one, the core of the cosmic reshaping. Paper 3, special relativity. This is what forever entangled our understanding of space and time.
The context here was a deep, deep problem in physics. Maxwell's equations for electromagnetism worked beautifully, but they clashed with classical Newtonian mechanics when things started moving close to the speed of light.
Right, and scientists had spent years looking for the luminiferous ether, this invisible medium they assumed light waves needed to travel through.
And the famous Michelson-Morley experiment failed to find any evidence of it. It was a huge puzzle.
And Einstein's genius was not trying to fix the ether.
No, his elegance was to strip it all away. He boiled physics down to just two simple, almost brutal postulates, and in doing so, he eliminated the need for the ether entirely.
What were those two postulates?
The first is the principle of relativity. The laws of physics are the same for all non-accelerating observers. Simple enough.
Okay.
But the second, and this is the truly revolutionary one, is the constancy of the speed of light. The speed of light in a vacuum is the same for all observers, no matter how fast the light source is moving.
That idea just completely shatters common sense.
It does.
If I'm in a car going 50 miles per hour and I throw a ball forward at 50, someone on the side of the road sees it going 100.
Right.
But if I turn on my headlights, no matter how fast I'm going, that same person on the side of the road sees the light moving at exactly the speed of light.
Precisely. And if that's true, then space and time cannot be absolute, like Newton thought. They have to stretch and shrink relative to your motion to make that light speed measurement constant for everyone.
Because that leads directly to things like time dilation, time slowing down, and like contraction.
Exactly. They become real physical phenomena. And that new mechanics, consistent with electromagnetism, was special relativity.
Which then gave birth to the most famous equation in all of science. Paper 4, mass-energy equivalence, EMC22.
This was a short paper published a bit later in 1905, and it was deduced as a direct consequence of special relativity. It states that the energy of a body at rest equals its mass times the speed of light squared.
And the power of that simple equation comes down to the sheer size of sea level. It's a colossal number.
An almost unimaginably large number. And it means that mass isn't just matter. Mass is literally a measure of energy content. If a body gives off energy, say, as radiation, its mass diminishes by a tiny, tiny amount.
But because you're multiplying by sea level, that tiny amount of mass converts into an extraordinarily large amount of energy.
Millions of times more than in a standard chemical reaction. And that profound insight, that conversion of mass to energy, is what explains why nuclear reactions release such massive amounts of power. This paper from 1905 laid the groundwork for the atomic age decades later.
So the Annus Mirabilis papers are, without question, the foundation of modern physics. It's just incredible.
It's hard to imagine any other single person having such a profound impact on so many different fields in such a short time. It truly redefined his life and career, taking him from an obscure patent clerk to a celebrated academic.
But special relativity still had a major flaw. It only dealt with constant motion, and crucially, it left out gravity. Einstein knew the job wasn't finished.
Which leads us perfectly into part 3, reshaping the cosmos, general relativity, and beyond.
Right.
The path to general relativity, or GTR, was long and difficult. It took him another decade, until 1915. And the major shift here was moving from thinking of gravity as an invisible force, like Newton did, to understanding it as a consequence of the geometry of space-time itself.
This sounds almost mystical, but it's based on what Einstein called his happiest thought, the equivalence principle. Can you break that down for us?
The equivalence principle is the conceptual heart of GTR. Einstein realized that, locally, you cannot distinguish between two scenarios: being at rest in a gravitational field, like standing on Earth, or being uniformly accelerated in free space, like in a rocket that's constantly firing its engines.
Wait, so you're saying gravity isn't actually a force? If I jump off a building, I feel the pull of gravity, but Einstein says that's not a force pulling me down.
That's the revolutionary part. The feeling of weight is indistinguishable from the feeling of acceleration. In that rocket, if you drop an apple, it falls to the floor just as it does on Earth. So if acceleration and gravity are equivalent, then gravity isn't a force, it's just inertia objects trying to travel in a straight line through a curved environment.
And that geometry is what he called curved spacetime.
Exactly. The core concept of GTR is that matter and energy curve the space and time around them. The classic analogy is a bowling ball on a stretched rubber sheet. It creates a dent.
And other objects, like marbles, just follow the curve created by the bowling ball.
Right. They aren't being pulled by a force. They are simply following the straightest possible path, a geodesic, through that curved geometry.
So the planets aren't pulled by the sun. They are just following the curve that the sun's massive presence has imprinted onto the fabric of spacetime.
That is precisely the GTR explanation. And this new picture wasn't just, a philosophical change. It made a concrete prediction that was better than Newton's. It provided the correct, precise explanation for the weird wobble in Mercury's orbit, something Newtonian physics could never fully account for.
And the math for this was extraordinarily difficult. We mentioned he had to get help.
He certainly did. The field equations were incredibly complex. He had to work closely with mathematicians like Marcel Grossman to handle the advanced calculus required, and he worked with his friend Michel Besso again to try and calculate Mercury's orbit. The math involves something called a metric tensor, a 10-component object that lets you measure distances in a flexible, four-dimensional geometry. It's really tough stuff.
GTR doesn't just describe our solar system. It predicts these cosmic behemoths at the very edge of reality. Let's talk about black holes and wormholes.
Black holes are a direct and profound prediction of GTR. They are regions where spacetime is curved so severely by mass that nothing, not even light, can escape once it crosses the event horizon.
And these aren't just theoretical curiosities anymore. We know they exist.
We do. They are fundamental components of the cosmos. We think they power things like quasars, which are some of the brightest objects in the entire universe.
But how do astronomers actually weigh something that is, by definition, invisible?
We watch the stars orbiting it. In the center of our own Milky Way, we have a supermassive black hole called Sagittarius A star. It's about 4 million times the mass of our sun.
And we can see stars whipping around it at incredible speeds.
Exactly. By observing the orbits of those S-stars and applying Kepler's third law, astronomers can precisely calculate the mass that has to be concentrated in that tiny, dark spot at the center. The black hole's gravity dictates the orbits, even if we can't see the hole itself.
And what about the science fiction favorite, wormholes?
Also a consequence of the theory. The idea of a shortcut through space-time, an Einstein-Rosen bridge, was described by Einstein and Nathan Rosen in 1935.
But is it possible?
Well, theoretically, yes. But to keep a wormhole stable, you'd need something called exotic matter with negative mass or energy, which we haven't found and isn't really feasible with any known physics. So for now, it's still in the realm of theory.
Okay, finally in this section, let's talk about what Einstein once called his greatest blunder, the cosmological constant, or lambda.
The story of lambda is one of the great ironies of physics. In 1917, Einstein added this term to his equations because the prevailing view at the time was that the universe had to be static and unchanging.
But his own equations predicted a dynamic universe, one that was either expanding or contracting.
Right, so he put in this mathematical fudge factor, lambda, to basically act as a repulsive force to counteract gravity and hold the cosmos still.
Then Edwin Hubble came along and showed the universe was in fact expanding.
And Einstein dropped the constant, calling it his biggest mistake. He felt he'd been driven by philosophical bias, not physics. But, the story doesn't end there.
No, because lambda has had this unforeseen renaissance.
A huge one. Since the late 1990s, observations have shown that the universe's expansion is not just happening, it's accelerating.
And this acceleration is being driven by a mysterious force we call dark energy.
And here's the profound twist. The cosmological constant has been revived because it acts as a measure of the energy density of empty space, which is our best working definition of dark energy. The term Einstein invented to hold the universe still is now the very term that explains its accelerating expansion.
It's just amazing that what he threw away as a mistake is now the central component defining the ultimate fate of the universe.
Absolutely. It means his discarded term is now thought to describe something like 70% of the entire energy content of the universe. It's incredible.
We've covered the man and his revolutionary breakthroughs. Let's connect all that abstract physics to our daily reality in part 4. Einstein's enduring legacy and real-world impact.
And the most direct, undeniable application of both special and general relativity in our daily lives is, without a doubt, the Global Positioning System, or GPS.
This is truly phenomenal. Most of us using a GPS app to navigate have no idea we're relying on physics that completely shattered Newton's laws over a century ago. So why is relativity so essential for it to work?
Okay, so to get your position, your phone needs to measure the time it takes for signals to arrive from at least 4 different satellites. And to do that, you need incredibly accurate atomic clocks.
Accurate to like, what, a quadrillionth of a second?
Something like that, yeah, 10, 15. But here's the problem. The clocks on those satellites run at a different speed than the clocks down here on the ground. And it's because of 2 relativistic effects.
The first one is from special relativity and has to do with speed.
Correct. The satellites are moving really fast, about 3,500 meters per second. Special relativity says that fast-moving clocks run slower, so that speed causes the satellite clocks to lose about 7 microseconds every day compared to us.
But then there's a second effect from general relativity, which involves gravity.
Right. General relativity says that time speeds up in weaker gravitational fields. The satellites are way up high, about 20,000 kilometers away, where Earth's gravity is much weaker. This causes their clocks to run faster than ours.
By how much?
By about 45 microseconds a day. This effect is much stronger than the speed effect.
So you have one effect slowing time down and a bigger one speeding it up.
Exactly. You combine the two, and the net result is that the satellite clocks run about 38 microseconds faster every single day. If the engineers didn't correct for that, the positional errors would build up so fast that within minutes, the whole system would be useless. You'd be off by hundreds of meters.
That's staggering. So the engineers have to build both 1905 and 1915 physics into every single device and satellite. It's just baked into the system.
It's completely baked in. In some systems, like the Russian GLONASS, they actually set the clocks to run slightly slower on purpose before they even launch them, just to preemptively cancel out the effect.
Beyond GPS, Einstein's influence pops up in some really surprising places. He wasn't just an abstract theorist.
Not at all. He was a prolific inventor involved in up to 50 inventions, some of them patented. He designed a gyro compass, a camera light meter, and most famously, a refrigerator.
Tell us about the refrigerator. That's a fascinating story.
Well, in the 1920s, he and his former student, Leo Szilard, developed several designs for a refrigerator that had no moving parts. It used an electromagnetic pump. They were motivated partly by a news report about a family that died from a leaky conventional refrigerator.
So they wanted to make something safer.
Safer and more efficient.
Yeah.
It wasn't a commercial success, but the design was incredibly innovative. It just shows his drive to apply fundamental physics to solve real, everyday problems.
And his theories impact fundamental reality, even at the atomic level, which is a mind-bending crossover into chemistry.
Absolutely. Relativistic effects influence the electron configurations in heavy atoms.
And how does that work?
Well, in really heavy atoms like gold or mercury, the electric pull from the massive nucleus makes the innermost electrons orbit at a significant fraction of the speed of light.
Wait, if the electrons are moving that fast, what happens to them according to special relativity?
Their effective mass increases, and their orbits actually contract and get tighter. This relativistic contraction changes the energy levels and bonding properties of the whole atom. And this is the key to why mercury is a liquid at room temperature, and also why gold has its unique yellow color.
So the color of gold is a direct, measurable consequence of immensity R influencing chemistry.
It is. It's incredible.
What about in astrophysics, beyond black holes?
GTR gave us the indispensable tool of gravitational lensing. The theory predicted that massive objects would bend light, so a huge galaxy cluster can act like a giant magnifying glass, bending the light from even more distant objects behind it.
And astronomers use this all the time now.
It's an everyday tool. We use it to find distant exoplanets and, crucially, to map the distribution of dark matter, which we can't see otherwise.
And going back to those impossibly precise clocks, GTR is now offering a new level of precision in just measuring our own planet.
Yeah, the developing field of geodesy. The newest atomic clocks are so precise they can literally measure height differences based on the time difference predicted by GTR.
How small a difference are we talking about?
A height difference of just 1 centimeter on Earth's surface affects timekeeping detectably. Time flows ever so slightly slower the deeper you are in a gravity well. So a clock at the bottom of a staircase runs marginally slower than a clock at the top.
So in the future, your phone won't just know your location. It'll know your exact vertical height down to the centimeter, just by measuring this tiny difference in gravitational time distortion.
That's the potential. His legacy is literally influencing how we measure the ground we stand on.
The influence is just pervasive. But let's return now to the philosophical man, the political and moral man.
Einstein's philosophy was deeply tied to his political engagement and his resistance to authority.
His political ideal was distinctly democratic.
Very much so. He said, "My political ideal is the democratic one. Everyone should be respected as a person and no one idolized." And that belief really fueled his deep commitment to human rights.
He was known globally as an instinctive pacifist, especially after World War I.
He was. He believed that a person for whom spiritual values are the highest must be a pacifist. But his pacifism wasn't passive. He called for active participation in the fight against war.
Which makes his involvement with the atomic bomb such a profound and uncomfortable paradox.
It's the ultimate contradiction in his life. Despite his core pacifist beliefs, he signed that famous 1939 letter to President Roosevelt urging the U.S. to pursue the bomb.
Why?
It was driven solely by a genuine, terrifying fear that Nazi Germany was on the verge of developing one themselves. He felt compelled to act against his own moral instincts out of a terrible necessity.
And then after Hiroshima and Nagasaki, he immediately became a tireless global advocate for nuclear peace.
Immediately. He co-founded the Emergency Committee of Atomic Scientists to advocate for peaceful use of atomic energy and warn the world about nuclear proliferation. He lamented that the bomb had changed everything except our way of thinking.
And his views on morality itself, he separated it completely from any divine origin.
He did. While he thought the pursuit of moral action is the most important pursuit of human beings, he also stated plainly, there is nothing divine about morality. It is a purely human affair. He saw it as something that evolved from our social needs.
That profound sense of striving for unification in his science and his life, that same drive continues to define the future of his field. Let's look at Einstein today and the future of physics.
Well, the central unifying challenge in physics today is the same problem that consumed the last decades of his life, unifying general relativity and quantum mechanics.
And we are still stuck on this fundamental problem over a century after he started it.
Yeah.
Why is it so hard for these two theories to talk to each other?
They describe the world in fundamentally incompatible ways. GTR describes the very large stars, galaxies, as a smooth, continuous fabric of space-time. Quantum mechanics describes the very small particles and forces in discrete, probabilistic packets.
And when you try to combine them, like in a black hole or at the Big Bang, the math just breaks.
It breaks down completely. So GTR, a classical field theory, stands alone among the four forces of nature, which is deeply unsatisfying for physicists who believe in a single, unified reality.
And the existence of black holes really highlights this crisis.
Yeah.
There was that famous bet between Stephen Hawking, Kip Thorne, and John Preskill about the information paradox.
Right, the question of whether information that falls into a black hole is truly destroyed forever, which would violate the laws of quantum mechanics. Black holes are the ultimate battleground where GTR and QM clash.
And Hawking eventually conceded the bet, didn't he?
He did. He acknowledged that quantum principles must win out, which implies that even GTR will eventually have to be modified or replaced by a deeper theory of quantum gravity.
Plus, modern cosmology requires us to accept things we can't see or understand, like dark matter and dark energy.
That's right. The fact that the universe seems to be made of 95% unknown stuff suggests that even Einstein's masterpiece, GTR, may not be the final word on gravity. There are still fundamental concepts we haven't grasped.
What a monumental figure. We started with a patent clerk, fueled by sheer curiosity, and ended with a theorist whose vision still guides our understanding of everything from, the color of gold to the accelerated expansion of the entire cosmos.
The legacy is truly dual. On one side, you have the genius who rewired the laws of the cosmos in 1905 and 1915. And on the other, you have the thoughtful, sometimes weary philosopher who mused on humanity, justice, and the strange burden of fame.
His wisdom extends far beyond physics, too. We should take his advice for leading a fulfilling life to heart.
I agree. His guidance was simple. If you want a happy life, tie it to a goal, not to people or things. His goal was the passionate search for truth and knowledge, and that resulted in a legacy that continues to drive discovery today.
So here's the truly provocative thought to take with you. We rely absolutely on Einstein's theories, especially GTR, for essential modern technology like GPS. Yet GTR itself points to its own profound limitations at the edge of black holes and requires the existence of these unknown forces, dark energy and dark matter, to make sense of the universe we see.
Which raises the most important question for the future of physics. What new aha moment, a spark of genius beyond GTR, maybe one that finally unites gravity and quantum mechanics? What will be the next profound shift?
And when that new theory emerges, how much of our seemingly stable everyday world, which currently runs on Einstein's rules, will that new understanding inevitably transform? It took almost 2 centuries to move beyond Newton. How long until we move beyond Einstein?